I'm Sarah Richards, and I'm a 15-year-old sophomore at the Charles City High School. My favorite subjects in school are science, math, and art. There aren't a lot of topics that cover all of those. However, fractals, that I did my independent study on, cover all those topics. So I was very interested in those, and I decided to pursue that. An independent study is a graded class that is offered at the Charles City High School to tag students. It's project-based, so you have to make a product and turn it in at the end of the trimester. And it's based off the 20% project at Google. The 20% project is a project where employees are asked to spend 1/5 of their time exploring an interest or just tinkering and seeing what they come up with. It's time to pursue your interests and explore. I did my independent study on fractals. Fractals are self-similar patterns that occur in nature and in math or man-made. They have patterns that repeat over different scales. So like this here, there's these 4 shapes and they change to become complex and very intricate and fancy. Here are just a bunch of examples of fractals. There are frost and snowflakes, which are probably the most recognizable one, because they're very fun to use in elementary school. These two right here are spiraling fractals, and I'll get more into those. This shows the scalability of fractals. It's very hard to know how big those rocks are, because rocks look the same over different scales. They could be really tiny rocks, or they could be giant boulders, and you wouldn't even know. These show how fractals cover a lot of area. In this first one of the river, you know that the rain has to fall over all of that area in the picture. However, it all drains into this one big river. Also, this is a human lung. The lung takes up a ton of space, and all these little branches can diffuse oxygen into blood. In the first 2 weeks of my independent study, I looked at types of fractals. The Coke snowflake is one that I looked at and went more in depth in. It's made with equilateral triangles, and you can see the very fine detail along the edges. Sierpinski's triangle also uses equilateral triangles, and it also gets incredibly tiny detail. The Coke snowflake and Sierpinski's triangle were 2 that I explored further and made out of clay to see how fractals can go on indefinitely. The Apollonian gasket is a shape drawn, and the biggest possible circle is drawn in it over and over. You can see that these circles get tiny as they go on infinitely. The Mandelbrot set is made with I, the square root of -1, and it's very complex and pretty. All these black points are the points in the set. And all the colored things are just showing different values. You can see that this general shape is repeated. The seahorse valley is between the head and the body, so that'd be in this little area right here. And this is a close-up of the seahorse valley. It's just very spirally. Pythagoras' tree is made by splitting a square or line or something. You can see that here. It splits and splits. Also here. It's just very full of spirals. Because you can see here, it just goes spiraling. The Fibonacci sequence is what I explored in week 3. It's a set of numbers. You can see here at the bottom. The last number and the number before that equal the current number. So like 1 + 1 equals 2. 1 + 2 equals 3, 2 + 3 equals 5, and so on. This forms the golden spiral. That is boxes of the Fibonacci sequence. It's like the area of this is 1, area of this is 1, area of this is 2, 3, 5, 8, 13. And then you take a curve and just draw it through it. So it ends up making this big spiral. This is used often in art projects. You can see it in the human ear, in plants, in the spiral galaxy, in seashells, and flowers. It's in a lot of places. The ratio of the current and last number in the Fibonacci sequence is closer and closer to phi. Phi is 1 + the square root of 5 divided by 2. and is equal to approximately 1.618. It's known as the golden ratio. You can see here how phi and the Fibonacci sequence are related. 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, and so on as it gets closer and closer to 6.18. The golden spiral is in plants. In this animation, you are a sunflower, and this value right here is how far you go before putting down your next seed. To demonstrate, if you go 3/4 of a turn, 0.75 revolutions before putting down your next seed, you end up with this. So you go from here to here, down the seed, all the way to here, down the seed, and here, down the seed. So if you look at this and try different values for a half turn for the next seed, you end up with a lot of lines. So if you're a plant, you want to get as many seeds as possible into the smallest area possible. With this, you have big gaps. You could be putting seeds. If you're a plant, that's just not a good formation of your seeds. And if you try different values, they all end up with lines and stacks of leaves. However, if you try phi minus 1, you end up with a lot of seeds packed into a small area. So, rational numbers end up in lines, and the leaves eventually stack. If you use 0.618, which is phi minus 1, you end up with all those seeds packed into a small area. So that's very good. In degrees, that's about 222.5. And that's that fraction, 0.618 times 360 degrees. So the benefits of the golden ratio: it will get more water to the roots of a plant, you'll get more sunlight on leaves because they cover more area, and you'll have seeds in less area. Then I looked into applying all these things that I had learned. I thought that a solar panel using a plant structure could be better than normal designs today, which normal designs today are just a giant solar field, which takes tons and tons of space, or solar panels on a rooftop. In weeks 4 and 5, I measured ratios of plants. I looked at the descending length of leaves, so the length of the leaf at the top of the stem going down to the bottom. And I looked at the distance between leaves, so the little stem portions in between leaves, and the angle of leaves from the stem. So the leaf is here, and this is the stem, this is the angle here. I also looked at the ratio of the length of a leaf to the stem below it. I had lots of help from teachers with materials and with plants to measure. I made a lot of calculations. This is the math part of this independent study. And I made all sorts of charts and graphs. This is just to show that there were a lot of calculations. I found that the descending leaf length was about 1. I rounded that to be a very pretty whole number because it'd be very hard to find small solar panels with small differences in size, because that's what I was going to need for this project. I found that the distance between leaves was about 1, that the angle from the stem was about 135 degrees, and that the leaf to stem ratio was about 0.7. Throughout this, I've been developing sketches and sort of transforming this crazy, hazy idea that I had into something that could actually work. So I developed these with the shop teacher here, Mr. Nielsen. He works with metals. And this is just a picture of all these scribbles I had. It was very messy at the start. Then once I had an idea of what I was going to do, I started building. I had a flat design, so that would be my control group, and that was a house with solar panels on the roof. And then I had a fractal-based design. I had lots of help with this, and it took lots of time. For the control group, I made measurements, cut pieces of cardboard out, then glued them together, and then painted them to make a house. Here's more pictures of me painting. And then I put solar panels on the roof. For the fractal design, I cut these little pieces of metal that would be welded onto this tube. Mr. Nielsen helped me make marks of where to put the little pieces of metal on the tube. That was very hard. This is some calculations that were just drawn on a whiteboard. This is me welding on the pieces. I cleaned it up with acetone and painted it red. Then, with the base completed, I started on the solar panels. I made a series circuit and then I taped them on because I wanted them to be removable to use them for different projects. Once I had everything done, I went and tested them. These are just my coordinates. It was about 0 to 15 degrees Fahrenheit over the day. The sunrise was at 7:20 and the sunset was at 5:30. It was very sunny the first day, but cloudy the second day. I used 2 different voltmeters. They were within 0.3% of each other, so that was very accurate. On day 1, I found that the rooftop design and the fractal design differed by 0.07 of a volt. Here are the graphs. So you can see it was very close. On day 2, I found that they differed by 0.04 of a volt. Again, it was very close. They stayed with each other for most of the day. However, I wasn't just looking at the volts produced, I was looking at the entire design. The standard rooftop design was not expandable. Once you put a solar panel down on a roof, you cannot build above it. That space where the solar panel is not usable anymore for anything but the solar panel. And around it, you can't have trees or tall buildings, because those would cast a shadow on the solar panel. However, my fractal design can grow upward. Space usage. The standard design can be put on rooftops, which saves space. However, the fractal design can grow upward, and the space underneath is usable. So you could have a park or something underneath this fractal design. They produce about the same amount of voltage. The cost of the standard design would be only the panels, and the cost of the fractal design would be the panels and a frame. However, the fractal design can be made to work with other things, like a telephone pole. For the area, I used 2x2 panels and 5 of them, so my standard design took up 20 square inches of space on a rooftop. However, my fractal design had a 3-inch in diameter pipe as its base, and that took about 7 square inches of space. So that was far less space taken up. With the same amount of voltage produced, less space used, and it can go upward, I'm going to have to say that my fractal design is better. So what's the point of this independent study? It's to make students self-reliant. I had to do a bunch of things myself, and I had to look up a bunch of information myself. The point of this project is to solve global problems. We're in the middle of an energy crisis, and we're running out of fossil fuels. My project, and others like it, can help solve this problem that we have, and independent studies can help solve other problems in the world. I mean, the next generation of high school students is going to need to solve these problems, and independent studies can help make them able to solve these.